we are still talking about attention. Okay, in this case, it's attention across the decoder and the encoder, right? Right. So then we'll start talking about other things, including self-attention. But what I will do is the following. Instead of telling you the self-attention right away, I'm going to try to generalize it a little bit, okay? To generalize the current attention mechanism and try to make it more general. So basically, we saw that in some applications, like the image captioning or natural language translation, these sort of the attention mechanism that I introduced, I'm sorry, not I introduced, right? Introduced by the community that I was just describing worked, right? Then one way of innovation is the following, right? You want to understand, right? So you could say, well, does the attention mechanism have to be like that way? Could something be more general or improved, or maybe the more general mechanism can be applicable to other tasks as well, right? So basically you want to see a bigger picture, right? It's like when you're playing a game and you're navigating in a very dark area and a lot of people are working together with you and they found some spots, right? So those spots gotta get a little bit brighter. Then you ask yourself, can we look even wider around those bright spots and maybe even connect the brighter spots together and making a bigger exploration of the space around us and figuring out how things work and how to make them work better, right? So that's what I'm going to do right away to generalize the attention mechanism before telling you about the self-attention, okay? So let's try to generalize the attention a little bit, right? There's a few slides I inserted last time. Let me see where I place it, because there's something I want to talk about. Okay, that's good. It's still several slides away, so I didn't skip those. So, okay, let's talk about how we can generalize things. Okay, let's see again. We have the hidden vector, right? Remember, back then I was plotting encoder-decoder, right? Encoder on the left and decoder on the right. And then every time I try to find the, the h, try to sort of figure out for h sub t, right? How much, to generate h sub t, right? How much I should, when looking at h sub t versus each x sub I or z sub I, the features, right? So how should I do the weighted average and how should I align them when generating the context? In other words, let me call this input x and their features z. And let me call the hidden state you saw before a query, because back then we were querying the similarity or the attention of, when using h over this feature z or the input x, okay? So I don't call it a hidden state for now. Okay, let's just call it a query. And later on you will see when we're talking about self-attention, this is essentially, the queries, okay? And let's talk about the operators we used. When trying to find out the alignment between the feature and the hidden vectors, now I call it a query. We said that back then this f sub att was approximated by MLP, and then I do a softmax to make this e's, right, normalized, right, between 0 and 1 and add up to 1, right? And then I have output. Back then I call it a context vector, right, which was time dependent, but now I didn't put h sub t, I just say any h. Let me call it a query, right? Previously you have a h sub t, which is a hidden state at time t for the decoder. But in general, let me just call it a h. It's called a query. And then I have this context I said before, which is, again, a weighted sum over all the features, zij's, right? And then you have these, this is a two-dimensional case, so I have I and a j. And I have this aij, which add up to 1 over all the ij's. And then I just use this convex combination of the zij, the features, okay? Okay, so you have the input that goes through something and x, and you go through some encoders, and you get z, okay? All right, so that's what we talked about before, right? So we're trying to start from the input, the query, and the features, z or the x before z, and our desired output is the context vector c, okay? I removed the time t here because this is more general than just the decoder we have seen before. So now, something you have to pay attention, is that this one actually, this attention mechanism is permutation invariant. In other words, if I just swap the order, right? I change the order, and then the corresponding weights would be changing the order as well. But in the end, it's because it's a weighted average, it really doesn't matter. So in other words, I can change x0, x1, x2 to x0, x2, x1. And the resulting A will be, A0, A2, A1, but the resulting C will be the same because, I'm using the weighted average, which is insensitive to the order of I, okay? That's something that you have to pay attention to. That's why I'm saying this attention operation is permutation invariant, right? Okay, so first thing that when we are trying to generalize attention mechanisms, I told you before, was instead of using the first one is on the alignment. So instead of using f sub att, which is usually parameterized by MLP, right? People found that actually we could have used a very simple parameter-free dot product, right? So there's no parameter. It's very easy to calculate, and it's dot product. When I say it's easy to calculate, I mean in the eyes of GPUs, right? Because this dot product, this kind of linear algebra matrix multiplication, parallelizable through different threads, is very easy, right? We'll mention in a few slides how we go through this, Q, K, V thing for the transformer. But before then, just think that, well, this is something that actually works, which is much simpler, right? This is very empirical discovery, right? But I think also when you have a data deficiency issue, depending on your input size and output size, these additional parameters in the f sub att may not be desired, right? But this is one empirical discovery. So the first change, replacing the MLP alignment function by simple dot product, okay? It's a similarity, basically. Okay, it's a similarity between the query and the input, okay? All right, so here I just use the input. I didn't use the features, okay? It would be the same because they have the correspondence. A small change here is that instead of using the simple dot product, I'm gonna use a scaled dot product. Meaning that I'm gonna divide this dot product by the square root of the dimension, right? So there are a couple of reasons of doing that, right? The first of all is that if you think about these softmax, right? It has exponential of one term divided by the sum of the exponential of many terms, right? Sum of many terms of exponentials. So if your dimension of h or x sub I, right, is high, right? So this softmax can easily get saturated, meaning that some dimensions can very easily dominate these softmax. Then this creates the vanishing gradient problem that we talked about, right? Right. So that's what I was talking about. The large magnitude vectors will produce much higher logits. Okay. So this post softmax distribution has lower entropy, and this can be causing these softmax to peak and vanishing gradient vanishing problems for other terms, right? And we can reduce that by simply using the square root of d. Okay, right? So this is one of the reasons, right? Okay, that's the first change. Instead of using the MLP for the alignment, we use a parameter-free scaled dot product, okay? So the second thing is the following. We used to do the following, right? We have a query, right? We have a query and we have the corresponding output, right? So back then we're doing like a single query vector a time. So another change here is that instead of looking at this single Q and output is a single Y vector, we can actually do it over multiple query vectors. Okay, so we can use multiple query vectors, and we'll talk about that as well. Okay, so in this case, this is the second change we'll make to make it more general. And then and the second and the third thing we're talking about is the following. So let's take a look at this input vector, right? So this input vector is used, right? Is used in both alignment, right? The alignment was here, right? And the attention calculation, right? So it's used in both alignment attention calculation. And if we want to make the model more expressive, right? We could add an additional step. So between alignment and attention, right? Between the alignment and attention, right? So we have this alignment EIJs, right? And we can calculate the attentions. We could add an additional layer like fully connected, right? Very easy. So that we don't use the same input vectors in both steps, right? Because in the first step of alignment, xi is used, right? But in the attention step, it will be transformed using the additional layer. So that's another thing that can be made more general, right? Okay, so now we're talking about this major split. In other words, you have an input vector, true, right? But this input vector was, as I said, used in both alignment and attention calculation. So can we split them by introducing these additional fully connected layers? In other words, right, I will convert the input to key using these parameters W sub k, right? I will convert the input x to the value vectors v using these additional linear vectors, linear matrices, linear operators, fully connected. So matrix W sub v. So I'm going to use the keys and the values in these two separate calculations respectively. So I'm not using x in both. I'm using linearly transformed x called keys and values respectively in these two steps, okay? So now you see that I split that input vector who was participating both steps into two vectors, keys and values, okay? So now you see that later on we'll talk about the transformers. Now you see that for our input, we now have what? Queries, but then our input vector x is essentially split into key and a query. So the transformers use key, value, and queries a lot. Okay, so that's another change, right? We talked about this alignment function, right? No longer parameterized, right? And we talked about this input vector now split into keys and values, which are to be learned. Remember, these W's are to be learned, right? And these keys and values participate in these two steps, alignment and attention calculations, respectively. Okay? So that's what we have here, right? So now that's what we have here, right? So now the input and output dimensions can also change depending on the key and the value FC layers, because I'm not using X anymore, right? So I could change the values and the key. I could change the X into keys and the values, and I can also change its dimension, not only the value but also the dimension as well. So so that's why we have, now the changes, right? So the queries are actually of shape m by d sub k, which is the key dimension, right? It's no longer the input dimension d anymore, right? So because, as we said, this is participating in the alignment, right? So its dimensionality is determined by the key dimension, right? And the output is using the value vector, right? So that's why its shape is d sub v, the dimension of value vector, okay? So notice that this the input and output dimensions can now change because I'm not using x anymore, right? Toward the input, I'm using key, and toward the output, I'm using value vectors, okay? Any questions so far? Any questions? Okay, so what is our query, right? In our previous example, right? So our previous example, the query vectors are h sub t, right? For instance, in the first time point, it's h sub 0. Because we were attending on the feature vector, right? Where we are trying to find the alignment between the hidden state in the decoder and the feature matrix from the encoder. That's what we are doing, right? Where Z is the spatial CNN features and FW was an MLP. So now it's much more simple, right? So it's just a dot product, but the calculation of the alignment and the attentions are now more complicated because I don't use X directly. Okay, I use key and values, which are to be learned. And so that's what we talked about before, okay?